This is a CRP-5 computer. Let's learn how to use it. Hi, I'm Grant and welcome to the bonus class all about this thing, the CRP-5 computer. In the airlines, you're never going to use this thing, but it does have some good applications for light aircraft flying, and it's also a very handy thing to be good at for the ATPL exams. So this class I'm just going to be teaching you how to use the CRP-5 computer, and it has two sides. It has this side with a moving inner scale and a fixed outer scale, as well as a few windows for calculating airspeeds and density altitudes, and then it's got this handy little line so you can easily line up. I think the best way to explain a CRP-5 is just through physical examples, actually showing how to use it, because when you write things down, it's hard to remember for this sort of thing. So the first thing you can use it for is unit conversions. I personally prefer just to remember the unit conversions, such as 1 meter equals 3.28 feet, but we can also figure them out using the CRP-5 calculator. So let's take a look at that one I just said, the 1 meter equals 3.28 feet. What we do for our unit conversions is we line up the 1 on the inner scale, which is here with the arrow. We move it below the unit that we know and then go to the unit that we want, and we read off the value for there. So 1 meter, we put that underneath the meter, which is, where am I? Over here. So the 1 is under kilometers, meters, liters. It's under the 1. So that means that 1 meter equals 1 meter. That makes sense. And then to find the unit we want, we look under that unit and read off the value. The inner scale and the outer scale aren't linear. The gap between 1 and 2 is only this big, but then 2 and 3 is only this big, and it gets smaller and smaller as we go around the circle. That's how this thing actually works. You may have noticed I was saying 1 instead of 10, but this is because we have to think about the CRP-5 as calculating the ratios, and it's not calculating the values in tens, hundreds, or thousands. To explain how that works with the 1 meter example, I line up the 1 with the 1, and then I go over to feet, which is what I want, which are down here, keeping the inner circle not rotating. And we can see that if it's lined up, should be about there, that we're looking at on the outer scale, sorry, on the inner scale, 3.1, 3.2, just under 3.3. See the divisions 1, 2, 3, 4, and 5. So 3.1, 3.2, 3.3, just less than 3.3. We can call it 3.28. If we add 1,000 meters, clearly there isn't a 1,000 indicator here. So what we would do is we would divide by 100, use the 10 value, go over to the feet, see that it's 32.8 feet, and then we'd have to remember to multiply it by 100 again to get 3,280 feet. So let's do some more simple conversions. I'll pop the details on the top left up here of what conversion I'm going to do instead of just writing them down like I normally do. So the first one we're going to do is 4 nautical miles into meters. So what I'm going to do is I will rotate the scale under nautical miles, which is here. So that means I'm now converting nautical miles. That would be 1 nautical mile. I'm not looking for that, I'm looking for 4. So that's 1, that's 2, that's 3, that's 4. Make sure that's lined up perfectly with the nautical mile mark. And what was I looking at for in meters? So let's go around to meters, and we see that we're about 7.1, 0.2, 0.3, 0.4, 7,400 meters. And the actual answer, using the conversion, 4 times 1852 equals whatever the actual number is. And we can do it with volumes as well. So again, 16 imperial gallons in liters. So imperial gallons up here. That would be 1 imperial gallon, 111, Or we could say, yeah, that could be 10, 11, 12, 13, 14, 15, 16 imperial gallons lined up there. Okay, 16 imperial gallons. And then we're looking for the value in liters. Liters is underneath the 1 up here. We'll go around and we read that off the inner scale as 7.1.2, 72.5, 72.5, 72.6, something like that. And the actual answer would be up here, 16 times 5.46, and I'm sure it will be around the 72 marker. As I say, I prefer just remembering the calculations, but you can use a CRP-5 calculator for these conversions. It's just going to be a little bit harder to get it accurate. So if you remember, there are a few speeds in aviation that we have to consider. First, we have our indicated airspeed, our IAS, which we then correct for any instrumentation errors to give us our calibrated airspeed, our CAS, which sometimes is called a rectified airspeed, an RAS. If we then apply compressibility errors to that, which happen at high speeds, we get the equivalent airspeed, the EAS. And then if we also add any density errors onto that, we get our true airspeed. The other speeds we have basically is the Mach number, which is the true airspeed over the local speed of sound. Local speed of sound equals 39 times the square root of the temperature in Kelvin degrees. So we can use the CRP-5 to calculate a few of these things. You can see that on the outer scale up here, we have true airspeed, and then on the inner scale here, we have RAS/CS, rectified airspeed/calibrated airspeed. This means that we can convert between the two. We do this using the airspeed window, which is here. The true airspeed will rely on the pressure, altitude, and the temperature at that altitude. And that's basically what we put in this window, and then we compare the values from the inner and outer scales. So let's have a look at some examples. We're at sea level, temperature is -40, and the calibrated airspeed is 100 knots. What is the true airspeed? So we're at sea level. That means that we line up the pressure altitude times 1,000 feet is on the 0. Temperature is -40. Minus is this way, plus is this way. So -40 would be here. So 0 feet, -40. Calibrated airspeed, the inner scale, we're looking at 100 knots. So remember, it's only calculating the ratios. So we're doing 10, 100, and then the calibrated airspeed's on the inside. True airspeed is on the outside. Looking at the outside, looks like it's 90 knots. A second example, the airspeed, say we're at 20,000 feet, temperature's -50, the true airspeed is 270. What is the calibrated airspeed? So we follow the same principle. We first of all go over to our pressure altitude of 20,000 feet. So that's going to be up there. I've aligned the 0 with 20,000. Then we go to the temperature. -50, which is this way. That's -40 there, -45, -50 there. And then we have the true airspeed, which is on the outer scale, 270. 270 looks about there, lined up with the calibrated airspeed on the inside, 210 knots, 210 knots. The only trick with these conversions from true airspeed to calibrated airspeed, or the other way around, is when we have to consider the compressibility effects at high speeds, which high speed is considered when the true airspeed is over 300 knots. That's the figure to remember. 300 knots, then you've got to do this additional step. So to apply this correction for the compressibility effect, we use this comp correction window, compressibility correction window, and it tells us basically what we need to do. We take the true airspeed, divide it by 100, take away 3, and we move that many divisions, and it's to the left, so you'd rotate it like this. So I'll show you some examples of that. So say we're at 31,000 feet, temperature is -40, and the calibrated airspeed is 240 knots. What is the true airspeed? So 31,000 feet. Get that in our airspeed window first, all the way up to, where are we, 31,000 feet, align with the 0. Temperature minus 40. So that's 31,000 feet, temperature minus 40. Calibrated airspeed is 240 knots. Inner circle, 240 knots. And that is showing 400 knots on the outer scale. It's above 300 knots, so therefore we've got to do the correction. And remember to keep this thing stable when you're twisting it. We're looking at the true airspeed divided by 100. So 400 divided by 100, that's 4. Minus 3 is 1. We move that many divisions. So we're going to move 1 division to the left. It's going to be just above that next one, about there. And then we go back to the calibrated airspeed and read off the real value. So 240 knots on the inner scale here, keeping it nice and stable. 240 knots. It's going to be lower than 400 knots. That's 35, 36, 37, 38, 39, 392 knots, 393 knots, something like that for the true airspeed after the compressibility effects. And the inverse is also possible as well. You just apply the correction before. So at 25,000 feet, temperature of minus 25 and true airspeed of 550 knots, what is the calibrated airspeed? So line up the airspeed window with wherever we are. We're at 25,000 feet, oh, way back here, 25,000 feet, and the 0 are aligned. The temperature is minus 25, that's minus 10, that's minus 20, that's minus 25, and the true airspeed is 550 knots. So we're going to apply the correction before, because we have the true airspeed, and then calculate the calibrated airspeed. So the true airspeed of 550 knots, the correction will be 5.5, take away 3, and move that many divisions. So 5.5, take away 3, that's 2.5 divisions. We're going to move that many divisions. So that's 1, that's 2, say that's about 2.5 divisions. And then we read off the true airspeed, which was 550 knots. It's already been corrected, so we're looking at the outer scale, sorry. 550 knots, where are you? Over here. That's half the battle, is actually finding where the numbers are, because it's moving around the whole time. So 550, calibrated airspeed, looking at 3, 5, 3, 6, 3, 7, 3. We're looking at maybe 380 knots, 382 knots, something like that. We can also use the calculator to find out the Mach number. So the Mach number is the true airspeed divided by the local speed of sound, and the local speed of sound is equivalent to 39 multiplied by the square root of the absolute temperature, the temperature in Kelvin. So the CRP-5 takes care of this calculation for us. So basically what we do is, say we've got a sea level ice a day and a true airspeed of 529. What is 529 knots? What is the Mach equivalent? So we're looking for an airspeed. So what we've got to do is look in the airspeed window, but then we go until we see the Mach number index, which is here. We align it with the temperature because it doesn't really care about the altitude, but we know that a sea level day in ISA conditions is 15 degrees. So that's 10 degrees there, 15 degrees there. And then what we do is we look at the true airspeed on the outside, and we're using the Mach number index. The true airspeed on the outside was 529, 5, 10, 20, 9. And you can see it's lined up with the 8 on the inner scale. So our Mach number is 8. But it's clearly not 8. We're not flying at 8 times the speed of sound. I don't think very many things are in the world, if anything. So logically, we know that it must be less than 1. It's going to be 0.8. So our Mach number for the day at a true airspeed of 129 knots would be Mach 0.8. You can also do calculations around Mach number, such as finding the temperature. So the true airspeed is 480 knots and a Mach 0.76. Let's find out the temperature. So true airspeed of 480 knots. Let's get that on the outer scale. 4.64748 is about there, and 0.76, that's 71, 72, 73, 74, 75, 76. And then what is the temperature? We just go, oh, I've just moved it there. See, this is part of the problem, it just moves around. Hopefully yours is a bit less used than mine. Mine's very easy to move. So what was I? 480 knots. That's lined up there, cool. And 76.72345 Okay, then we go over to the temperature window, and we'd see that it's about 10 degrees, minus 10 degrees, sorry. And then you can also say that the local speed of sound on that day, if we line up with Mach 1, is going to be about 630 knots. There's a few other things you can do, but I think they're fairly easy to work out, such as this temperature scale at the bottom. So it basically shows Celsius on the top, Fahrenheit on the bottom. So you can see that 10 degrees Celsius is equivalent to 50 degrees Fahrenheit. And another fairly useful thing is the specific gravity indications around the here top. There's one for metric, and at the bottom here there's one for imperial units. So what we can do with the specific gravity is you put in however many liters you want under the liters, for example, and then you go over to the specific gravity on the scale and read off the value. So for 30 liters of fuel, which I have set under the liters, we go to a specific gravity of 0.8, and we can read on the inner scale that that's going to be 24 kilograms. Or if we wanted that in imperial units, again the same 0.8 density, we're looking at maybe 51, 52, 53 pounds of fuel in 30 liters at a specific gravity of 0.8. So by far the most useful application of the CRP-5 is on this side, for calculating winds and wind drifts and amounts and speeds and all this kind of stuff. You can follow a very specific pattern for the process of finding X equal do this routine, if you're finding Y do this routine. But I think there's kind of a better logical way to think about it, and that is using a triangle of vectors. So this triangle of vectors looks like this. Basically we fly a heading at a forward true airspeed. We're blown off by a wind which has a direction and speed of its own, and that makes us fly a track over the ground at a specific ground speed. And we drift off by an appropriate drift angle. And if we apply a correction that is equal and opposite to that, we'll maintain, we won't drift, we'll fly directly along the ground in the same direction that we. Wind can be broken down into two components. It can be broken down into a headwind component that blows us back and a crosswind that blows us on across. And depending on how angled to us this wind is, it will be different proportions. So in this example, it's all crosswind. We've got no element that's pushing us back because it's at 90 degrees to our heading. The CRP-5 can be used to calculate how much of a proportion of wind is headwind and crosswind. So you use the CRP-5 wind along with this card. It's got one that goes up to 300 knots and the other side goes up to 1,000 knots. So 300 knots should be useful for most applications. And it's got a bit at the bottom of it which is just a straight wind card. I suppose this is where you can put in your wind, and then once you know your speed you come up to the top. To break down a wind into its components, you need to first draw it on and see what happens. So although it says true heading up at the top here, think of this as being whichever one you've desired in that triangle. So if we put true heading at the top, we have to have the true airspeed down here. If we put the true direction of the wind, then it would be the wind down here, and then you can do logic checks to make sure that it's working out all right. So for this example, we're going to use a wind of 360 at 20 knots, and we're looking out for the crosswind component on a runway 030 degrees. So first things first, if you can, always do wind first, okay? That's the starting point, I would say. So at the top it says true heading. We don't want true heading, we want the wind at the top. So the wind direction is from 360, where are we? 360 is around here. We're lined up on the 0 point and it's blowing from 360, so it's going to come down the page. And it's going at 20 knots. So you will use a pencil, make sure it's nice and sharp, and hopefully you'll be able to see on this. It's at 20 knots. Draw a little cross, just see that there. And then you would rotate it round to whichever runway we're using. We're using runway 030. 030. So now we're looking at the heading, and we'd compare our crosswind and our headwind components here. So we can see that our crosswind, it's blowing us 5 degrees. These are every 5 degrees, these increments, off to the right. And the headwind component is maybe about 17 knots, something like that, just under 20, just under 18, yeah, 17 knots headwind and 5 knot crosswind. And then I would always do a quick error check to make sure that that makes sense. So this is our runway heading. Our wind is coming from this angle. It's coming off from 360. And if it's blowing from this direction, it's going to blow us slightly off to the right, which it is, and it's blowing into the nose of the aircraft. It's a headwind, which makes sense. So that's how we calculate the winds. When we have a forward speed, things become a little bit more complicated, but try and just remember that triangle of vectors and do the logic checks. So given a heading of 090, true airspeed of 150 and wind 060 at 40, what track is being followed and what is the ground speed? So first things first, we put in the wind. So 060 up here, wind 40 knots down here. And when we put the heading up at the top, we can see the drift and the head tailwind component and how that's relating to the true airspeed. So we pop that up at the true airspeed, which is 150 knots. Get that nice and precise. So we're on 150 knots on our true airspeed, but we've still got the wind at the top. So what we're going to do is rotate that to our heading of 090. And then we can see that the wind coming from 060 is blowing us off to the right, and it's going to slow us down a bit, which kind of makes sense. So drift looks like it's 9 degrees, 5, 10, yeah, 9 degrees off to the right. So our track would be a further 9 degrees right, or in this case it would be 99 degrees would be our track. And the ground speed looks like it's just below 120, maybe call it 118 knots. And then again, air check, the wind would push us off to the right and slow us down. So another example, heading 240, ground speed 150 knots, the wind 280 at 40. What is the true airspeed and drift? So we start with the wind if we can. So come down, put in the wind. Wind 280 at 40. Where's 280? Around here. And it's blowing at 40 knots, so it's down here. Make sure your pencil's nice and sharp for this. We then put our speed in at the slider. So in this case, it's a ground speed. So we've got 150 knots. And then we turn to our heading, which is 240. But this doesn't make sense because we've got our ground speed in here, but our heading up at the top, and the heading is matched with the true airspeed in that triangle. So this is all slightly wrong picture. But we do know our ground speed is 150 knots. So we can slide up this X until it's on that 150 degree line. Like so, we've got the cross on the 150 knot line. So our ground speed is 150 knots, that matches. And our heading's up the top. So we can see that our true airspeed in the middle here would be 178 knots. And the drift is 10 degrees to the left. So our track is going to be 240 minus the 10 because it's going to be over here. So track 230, true airspeed of 178 knots. And just the error check, let's go back to see what the wind is. 280 from this direction is going to push us off to the left with this heading, yep. And it's slightly from the front, so it's going to slow us down a bit, which makes sense. So another example, heading 040, true airspeed 120 knots, track 055 and a ground speed of 110. What is the wind speed? So in this example, you're almost doing it in reverse. We can't put the wind in first because that's what we're trying to find out. So let's do what we do after the wind normally. So we do wind and then we normally turn to the heading. So we've got that of 040. And we have a true airspeed of 120 knots. We'll slide up to that. So true airspeed and a heading at the top. Those two, that side of the triangle, true airspeed and heading. The track is 090. Sorry, the track is 055 and the ground speed is 110. So 055 is going to be a 15 degree drift to the right. So we're looking at this line here, this 15 degree line. And the ground speed is 110 knots. So it's 10 knots slower. So we're going to put a cross just here. And then we would bring it down to the wind and read off the wind. So let's go down to the bottom, align that with the nice 0 line. And then when this is lined up on that line there, that's our wind. So at the top, we can see that it's 336 and the speed is 32 knots. And then you could error check that again. So if the wind is 336 at 32 knots, then with a heading of 040, that wind will push us to the right onto a larger track, 055. Yeah, that makes sense. And it's coming slightly from the front, so it's going to slow us down a bit. Yeah, that makes sense as well. There's a few more variations to these wind calculations where you calculate different aspects of that triangle. And they're all fairly similar except for one, which requires a little bit more work. And this is where you have to find out the desired heading and ground speed in order to fly a specific track. So for wind speed 060 at 30 knots, track 090 and a true airspeed of 100 knots, what are the ground speed and the heading? So if we can, we put in the wind first. Then we slide ourselves up to the true airspeed, which is 100 knots, up there. And then we turn to a heading, which we don't know, or the next thing that is best is a track. So track 090. The problem with this is we're kind of mismatched with that triangle. We're reading a track up here, but we've got a true airspeed set in the middle here, which is off. We should have the true airspeed in the middle and the heading at the top. So we've got to do a bit of experimentation to get the correct heading at the top. We do this by reading the drift and seeing if it matches. So if we now think of this as a heading of 090, and we can see that our drift is maybe 11 degrees, and that would mean that our actual track would be 101. But we know that our track needs to be 090. So with a bit of experimentation, you can see how this works. So track we want 090, let's try a heading of maybe 075 because we know we've got to steer into the wind. So let's go to 075. So with a heading of 075, we have a drift of, what's that, 6 knots, 6 degrees to the right? Yeah, 6 degrees to the right. 75 plus 6 is only 81, so that's not correct either. If I go to 81, for example, we have a drift of 9 degrees, and the desired track we want is 90, which is 9 degrees more than 81. So this is properly aligned now. This all makes sense. So we can say that on a heading of 081, we'll have 9 degrees drift, which pushes us onto the desired track of 090. And our final answer would be a heading of 081 and a speed of 72 knots for the ground speed. That's the only one that's a bit difficult because you've got to do this adjusting and trial and error, but hopefully you see that it makes sense. You've got to have the track aligned up with the correct amount of drift, essentially. That's it as far as the CRP-5 goes. It's obviously, I've just shown a couple of examples of everything, but during practice tests and question bank exams and stuff like that, you'll become more and more familiar with how to use this thing, and it'll become second nature. Just remember about that triangle for the wind calculations and how to do your speed conversions, which error check you have to do, and that value of 300 knots for the TAS, and then you've got to apply the compressibility corrections.